Montreal today, so it's really terrible weather out there. Okay, well, it's 10 o'clock, so I think we'll go ahead and get started. Good morning, everybody, and welcome to this edition of Trainee Talks. This will be our last webinar before the summer break. If you're new to us, Trainee Talks is a series of research talks delivered by software engineering graduate students in the NSERC CREATE SE4AI program. Everyone is receiving specialized training in the technical and social aspects of AI-based software systems. My name is Lori Akiyama, and I'm the program coordinator. I'll also be moderating the webinar today. So today, I am very pleased to introduce two CREATE trainees who are nearing the completion of their master's studies. T. Van An Dao is a Master of Applied Science student in software engineering at Concordia University under the supervision of Professor Jin-Chi Yang. Anne's research focuses on reliable large language models for legacy software engineering, particularly COBOL code generation, compiler-guided feedback, and domain adaptation. She previously worked as an AI research engineer and continues to collaborate with Mila and McGill University on applied AI projects involving natural language processing and software engineering. Her interests span AI for software engineering, including code generation, program analysis, and the development of AI systems that improve software maintenance, modernization, and developer productivity in real-world enterprise environments. Today, Anne will be presenting her work on Towards Reliable Large Language Models for COBOL through compiler-guided feedback and domain adaptation. Immediately following Anne's presentation, we will hear from Yasmine. Yasmine Ben Braiek is currently a Master of Science student in computer engineering at Polytechnique, Montréal, affiliated with Mila Quebec AI Institute under the supervision of Professor Futs Kom. She is active in the research community and serves as an IEEE volunteer. Yasmine's research focuses on evaluating large language models for software engineering, with particular emphasis on code generation, software quality, and LLM as a judge approaches. Yasmine recently presented her work on XPJudge, explanation-aware pairwise judging for cost-effective code LLM selection at the International Conference on Software Testing, Verification, and Validation, ICST, in South Korea, and she expects to graduate this summer. So welcome to both of our students today. Each trainee will speak for 20 minutes, and then we'll have a 10-minute Q&A. This webinar is being recorded. I hope I'm recording. I think I am. And it will be available to view on our CREATE website at se4ai.org and on our YouTube channel. So with that, I'd like to turn things over to Anne.
Thanks, Laurie, for your introduction. Could I share my screen right now?
Yes, please.
Okay. Okay, can I start?
Yes, please go ahead. Thanks, Anne.
Okay. Hello, everyone. My name is Anh, and today I will present my current work, which is also my thesis, titled Toward Reliable Large Language Model for COBOL through Compiler-Guided Feedback and Domain Adaptation. This work is done under the guidance of Dr. Jin-Chu Zhang and Dr. Xinhui Tang. I would like to start with why COBOL still matter. COBOL is an old programming language designed 70 years ago, and until now, it still matters, it still powers many critical systems in areas such as banking, insurance, government, and enterprise computing. And there are still millions of lines of COBOL code that need to be maintained. But at the same time, organizations face two practical problems. First, the COBOL workforce is aging, and there is a shortage of experienced COBOL programmers. And second, many organizations want to modernize or migrate their system into the modern one. But this process is really expensive and difficult. Because of this, LLMs are a promising way to support COBOL maintenance and migration. So, does this really work? I'll show you two typical examples of problems in LLM-generated COBOL code. In the first example, it is missing the terminator and app. Even though that the logic here looks simple with an if-else statement, this code lacks a block terminators, resulting in a compilation errors in line 24. In the second example, it shows the incorrect use of built-in function. We can see that it's trying to use the mode function by use something like variable 1, mode variable 2, but LM use it incorrectly. The true ways is function, mode, argument 1, argument 2 like this. And on the right side, I also show the benchmark result on COBOL eval across different LMs. COBOL eval is the COBOL generation benchmark translated from human eval. And I'm using the CSR compilation success rate and PASAT1 as the metric. And we can see that even strong modern LMs still have low compilation success and low functional correctness on COBOL. So the central questions of this work is how can we make LMs more reliable for COBOL? We first jump into the field by analyzing the common compilation errors categories in LM-generated code. This slide compares the distribution of compilation errors in human-written COBOL and LM-generated COBOL on the right. The human-written COBOL is on the left. And there are two key observations we can get from here. First, incorrect use of program structures is more common in LLM-generated COBOL code than in human-written COBOL code. This shows that LLM struggle with COBOL conventions and program organization. And second, some arrow type are unique in LLM-generated code, particularly incorrect use of built-in function and incomplete block termination. This reflects the weakness of LLMs in COBOL semantics. The main takeaway here is that LLM can handle some basic COBOL construct, but they are still struggle with COBOL-specific structures and semantics. From this analysis, two main challenges become clear. The first one is reliability. Generated COBOL often fail to compile, contains a lot of errors, and even compilable code is still incorrect. Therefore, we introduce COBOL Assist, which is a sharp debugging framework using compilation feedback. We start with programming problems. The LLM first generate COBOL code. We then compile it using COBOL compiler. If the code is compilable, we keep it. Otherwise, we take the compiler feedback and send it back to the LLM and ask them to repair the code. This process repeats until the program is compilable or it reaches the maximum number of iterations. And the key idea here is that the compiler provides information of syntax errors, which is much more useful than asking the LLM to refine itself without any feedback. In the experiments, we'd like to show the effectiveness of COBOL Assist, and this table shows the result on COBOL eval in 3 settings. Without COBOL Assist means using LM to directly generate code. Zero-shot refinement is asking LM to fix the generated code without any feedback. And with COBOL Assist means using our framework. And across all the evaluated models, compiler guided repair improve both the CSR compilation success rate and PASAT1 more than zero-shot refinement. For GPT-4o, CSR improved from 41% to nearly 96%. There is a very large gain in compilation reliability. And should be noted that currently we only have mainframe, which is the open source LM trained specifically for COBOL generation. And when we use a mainframe to generate code and combine with ability of GPT-4o to refine, the CSR might reach up to nearly 98%. In the second table, I show the reduction in the number of compilation errors. And in the first column is the number of errors before and after going through COBOL Assist framework. For GPT-4o, it dropped from 243 to only 446 errors, with corresponding to an 81% reduction. And an interesting part in this experiment is we only need less than 2 routes to iteration to make the code compilable. So the main takeaway here is that compiler-guided feedback consistently outperforms zero-shot self-refinement and has ability to improve COBOL compilability. Although COBOL Assist might help in fixing code, it does not solve the broader problems of COBOL generation, as current LLMs are not good for COBOL. This is because we are lacking of high-quality data. The data in this field is limited in public sources, and practical COBOL code is kept private in the enterprise system. And the second challenge motivates us to improve the model performance using domain adaptation with curated COBOL training data. And this one is the data curation pipeline I use to collect COBOL specific data, which came from 3 sources. For the first source, we collect COBOL from public GitHub repositories. This pipeline starts with filtering and deduplicating the code. Then we feed it through COBOL Assist framework to make all the code compilable. From these validated programs, we can generate description and COBOL pairs that could be used for instruction tuning in a later step. And from this source, we collect around 31K samples, and we can see that that amount is not enough for training process. So we think about using synthetic data. In the second source, we address data through synthetic data generation. We start with Java programs, and then we use LM to translate them into COBOL. Then compiler-guided validation is applied, followed by similarity-based validation through back translation and AST-based check. And this step to make sure that the translated COBOL code is reasonably faithful to the original Java logic. And this source is important because it provides much larger scale than public COBOL alone. And in the third source, we focus on textual COBOL knowledge rather than executable programs. Here, I collect a licensed textbook and website, and I extract the content, segment it, and use LM to synthesize into question-answer pairs. This source help capture the conceptual explanation and mainframe-specific knowledge that might not be well represented in code alone. Fine-tuning on this curated dataset, we introduce an LM named COBOL Coder, a domain-adapted LM for COBOL. And this model is trained on top of Brain 2.5 Coder. It is designed to support 2 tasks, COBOL generation and Java COBOL translation. In the experiments, we report the performance of various LM on 3 benchmarks. 2 first benchmarks are COBOL Eval and COBOL Code Bench, which focus on COBOL code generation. And on the other hand, although migration is an important task, it is underexplored in research, and there is no existing benchmark in this field. Therefore, we introduce COBOL Java Trans, the benchmark specific to bidirectional COBOL Java translation. About the evaluation result, we compare our LLMs to various open source model and GPT variants. We can see that COBOL Coder 14 billion reached nearly 70 3% CSR and over 49% Passat 1 on COBOL significantly outperform many open source baseline and even strong general purpose model like GPT-4o and GPT-OSS. Next result is on COBOL translation. We noted here C to J and J to C corresponding to COBOL to Java and Java to COBOL. And COBOL Coder again performs strongly, especially on Java to COBOL, which is more difficult direction. And this result can confirm that domain adaptation matters in this field. In addition to a benchmark result, we also evaluate the LLM-generated code with experienced COBOL developers by organizing a practitioner study. It includes three COBOL developers with different levels of industrial experience. This survey contained 10 tasks covering code generation, COBOL to Java translation, and Java to COBOL translation. And for each task, the participants are provided a task description along with three potential solutions from three anonymized LLMs. We consider three LLMs here, including COBOL Coder, GPT-4, and GPT-4o. And they are asked to evaluate three outputs and rank them based on the functional correctness, readability, and COBOL coding practice. And at the end, we also provide a list of open-ended questions to gather their feedback. And this is the result. COBOL Coders 14 billion version received 17 out of 30 first place rankings. Preference are also strong on Java to COBOL task, and this practitioner's result is consistent with our experiment result. The qualitative feedback is also very positive. Participants describe our LLMs are closer to the coding style that they use in daily work and better at reducing cognitive load. And that brings me to the end of my presentation. In this work, we study how to make LLMs more reliable for COBOL. First, we show that LLM-generated COBOL code exhibits distinct error patterns, especially structural and COBOL-specific semantics issues. Second, we introduce COBOL Assist, which use compiler-guided feedback to improve the compilation success and functional correctness of COBOL code. Third, we build a COBOL-specific data curation pipeline and develop a COBOL Coder, a domain-adapted LLMs that significantly improve COBOL generation and COBOL translation. And finally, the practitioner study confirmed that these gains are not only visible in benchmark, but also meaningful to experienced COBOL developers. And thank you very much for your attention. I'm happy to take your questions.
Thank you very much, Anne, for your presentation. I think we have a question from Jasmine, and then we'll have Bram, and then Rashna. Go ahead, Jasmine.
Thank you. Very, very interesting talk. It's really relevant for me because I work in a bank and we are currently trying to migrate a huge system written in COBOL. And I was wondering, how does this scale? Because right now I'm guessing it's benchmarked on little snippets of code, right? But usually those systems, they have like millions and millions of code. So how does this kind of approach scale to translate from COBOL to, let's say, Java? And is it possible to go from COBOL and extract business rules, for example, from the code itself? So yeah, that's my question.
Okay, for the first question, about the scale of this work. In this work, I mainly focus on the file level, but it's also one of my limitation. Like I only focus on file level, but it cannot capture the practical repository right now because the repository take so long line of code. Is the field that maybe I will explore more in the future. And for the second question, I don't clearly understand the your question, like how to
So
capture the business rule, right?
yeah, like any functions or rules in the code that can be translated into documentation, for example, instead of just code. Um, does this kind of approach also apply to that use case?
Like gen from the code, how can we like use
Generate
LLM to,
documentation from the code, from COBOL, for example.
yeah, like from code to text, right?
Yeah,
Yeah, it's another field. Like this work focus on code generation, like code generation instead
I
of
see.
text generation.
I see. Oh, thank you. That's great work.
Yeah, thank you.
Right. Yeah. Yeah. Great work. I agree, and I agree with Yasmin as well that yeah, there's a lot of companies. I mean, 20 years ago, I had a colleague doing a PhD who actually was also working on COBOL
Mm.
code to understand the business rules that are encoded in like millions of lines of COBOL code. Big problem. So yeah, I think looking into how the LMs could actually be used to extract their information instead of like generating code would actually be, I think, an interesting future work direction. But related to this, I was wondering because when you showed the results, you showed both the results of your LLM for Java to COBOL and COBOL to Java, but it seems that the GPT OSS model was actually quite good. The for COBOL to Java. Do you know why it is so good? Like
Yeah,
the
you are right.
Mhm.
Because we cannot access the data of GPT model, so we cannot say anything about that. But like from my experience, GPT OSS is quite good in this field.
Yeah, because arguably, I mean, a lot of companies want to, well, either they hire new COBOL developers or they somehow try to convert their code base to another language. So the COBOL to Java is maybe even the more important direction, I would say.
Mm,
So
right, right.
so it's important to figure out like what's happened. I mean, that's already good by default, so it's hard to improve it perhaps. So that's something. And actually, and maybe one issue, and maybe that's the strength of that GPT model is that for ages, the problem with COBOL code is that there's not just one COBOL language. There's like dozens of variants. Every proprietary compiler has their own variant of COBOL with different syntax, different features. So maybe I don't know. Maybe the GPTOS or the OpenAI people they have access to like a bigger, more diverse set of COBOL dialects in their training set, whereas in your case you have one specific case and maybe that's causing issues. I don't know. So maybe looking into diversity of COBOL dialects in your training set, maybe that could help you for especially for the COBOL to Java case.
Yeah, exactly. Because in my training data set, a large portion is from synthetic generation.
Mhm.
So it could be much better if we can access to like internal data from enterprise, something like that, to get
Mhm.
more diverse code.
Uh,
Yeah, or maybe figure out if there's different compilers online with different that support different variants. Maybe generate synthetic data for different
mhm,
variants,
mhm.
maybe of the
Mm,
language. Maybe that could
Yeah,
also help. But,
yeah, I think that's a
yeah.
great comment. Thanks, Brian. So I think in Anne's experiment, and feel free to correct me if I was wrong. But I think we particularly focus on one particular variant instead of going broadly, and that's a particular design choice we made earlier. And it's at the yeah, feel free to comment and follow up.
Yeah.
Because we decide on IBM COBOL, right? That's a specific variant, and Brian's suggestion is really good. Maybe going broad is just early design decision that we choose, but now maybe it's time, always good to revisit our earliest design choice. Yeah.
Cool. Cool. That's definitely a very interesting and an important problem. So I'm really interested in seeing how you guys proceed there. Yeah, absolutely.
Yeah. Thanks. Yeah. Great suggestion. Thanks.
Thanks.
Thank you very much, Dr. Adams, for that. Rashna, please go ahead. Nice to see you.
Thank you, Lori. Thank you, Anne. Great presentation and very nice results. Actually, I was very happy to see the results. And I was about to say what Professor Bram mentioned. Like in IBM, there was lots of projects only on moving COBOL based system to Java based system. Maybe that is also one of the reason that LLM has lots of representations and example for COBOL to Java. So that's the reason you found a high score on like GPT OSS and GPT-4o for this route of translation. But I was very surprised that the model did work. Your model did work very nice because I think COBOL and Java, they are different kind of language. One is object-oriented, Java, and COBOL is, I think it's procedural. So did you face any tweak that you had to do to fit your model to make the transformation from Java to COBOL?
I'd go back to the data curation pipeline.
Yeah.
Okay, this the previous slide is the one that I showed you, but it is the simplified version. This is the more complicated one that I use in my work, and go to this source tool, which is the synthetic generation. It's quite like complicated to translate from Java to COBOL. How can we make sure the quality of translated COBOL code is good enough? So in this pipeline, I first use the Java code, and then I use the COBOL assist to make sure that the translated COBOL code is compilable. And then I will go to stage 2, similarity-based validation. In this step, I use the original Java code and translated COBOL code. Then we use the LM to give a score for this pair to see the similarity between Java code and COBOL code. Then I use that COBOL code to back translate it into Java, and then I compare the back translated version of Java and original Java. Then we used an ASD-based checking and similarity scoring to give a score. And the pairs that that have score more than a threshold that we defined will be collected. That is the way to make sure that the COBOL and Java is correct.
Okay, so you use GPT or which LLM did you use, and you did not execute to see that okay the translation is correct or something, because maybe you are working on a file level code base, or I don't know.
Yeah, for the LM we use I choose GPT-4o because it is strongest model from my experience experiment. And what is the second question?
So you did not execute the code
Yeah,
that was
because
translated.
we only use compiler to compile the code instead of execute, because we don't have a test case.
Yeah.
If we
Okay.
have test case, that really good, but we don't have it.
Mm.
So that's
Nice,
why.
nice work. And okay, fine. Thank you. See you in the on 12th floor. Thanks.
Thank you.
Wow. Okay. Anne's talk is generating a lot of questions. We have time for one last very quick one from Jean Carlos, and then we're going to move on to Yasmine.
Thank you, Anne, for the great presentation. It was very nice. My question is about the first results where you plot all kind of type of errors. Could you go back there, please?
This one, right?
No, with the pie chart.
Okay.
Yeah. Is there some kinds of error that more persistent than others? For example, some kind of errors that even giving the compilation feedback, the model tend to not repair those kind of error. Then you reach the threshold attempts.
Yeah. That's a good question. This one is the pipe that compare human writing code, LM generated before COBOL assist and after COBOL assist. Actually, in the previous slide, I only showed two pipe here, but for your question, I will add more than that. With this pipeline, this pie chart is the distribution of common compilation errors in LM generated code after fixing. And we can see that a large portion of errors remaining is still about incorrect use of function correctness and of program structural and incorrect use of built-in functions. And we found out that LLM usually hallucinate the function that are common in other language to COBOL. For example, I have one here. Is this function is very common in Java and Python, and they usually use in this way. But in COBOL, the structure is different, and if the LM don't know about this information, it cannot generate the right one. That's why we still see the large amount of incorrect use of built-in function here, and also the program structure is important after fixing the code, the COBOL code.
Okay. Did you do many rounds of feedback or just one?
I use 3.
Okay.
In my pipeline, I also have an appendix about that, but like in the main experiment, I use 3 iteration. But in my experiment, they only need less than 2 rounds to finish that process.
You mean like having no error anymore?
Like the average iteration here. They only need less than 2 rounds to make sure that the COBOL generated code is compilable.
Okay.
But we said the maximum is 3.
Okay. Thank you. Thank you.
Thank you very much.
Thank you very much, Anne, for your presentation, and thank you everyone for such interesting questions. I'd like to invite Yasmine to proceed with her presentation next.
Hello, everyone. Thank you so much, Lori. I will share my screen. Is it good?
Yes, can you make it? Yep, there, that's great. Thank you.
Okay. Hi everyone, good morning. I am really glad to be giving this trainee talk today as a part of the CREATE SE4AI program, especially that now I am very close to graduating. Today I will present the main work of my master research titled XPJudge, Explanation-Aware Pairwise Judging for Cost-Effective LLM Selection. This work is about evaluating large language models for code generation and more specifically, how we can choose the right model. I will start with the motivation, then explain the problem, present the XPJudge approach, and finally discuss the main results and takeaways. What is the current situation? So today, LLM selection for code generation is still largely leaderboard driven. So when developers or researchers want to choose a model, they often look at public rankings and compare the models based on the execution-based scores. So in code generation, these scores usually come from unit test pass rates, like pass at 1, pass at k, and a model generates code. The code is executed against a predefined test, and the model is ranked according to how many tests were passed. So this is useful because unit tests provide an automatic and objective signal of functional correctness. However, this also means that model selection is often reduced to a single number. So the problem begins when we treat this number as the full picture and we tend to pick the highest ranked one, no matter what the cost is. So we need to look beyond leaderboard rankings. And why does this matter? Well, LLMs are increasingly used in software development, so either for completing code, debugging, refactoring, and understanding the software. So choosing the right model matters. It affects not only whether the generated solution passes tests, but also whether the code is understandable, easy to modify, trustworthy, and enough to integrate in a real project. There's also the cost dimension. So large language models often require more expensive hardware, more memory, more inference time, and a higher API cost. So if a smaller model can produce similar or better code for a given task, then always choosing the largest one is not necessarily the best decision. So the goal here is to work is to of this work is to support quality and cost-aware LLM selection by comparing near-tied models. So the objective is not to replace unit tests. Unit tests remain important. Instead, we complement the unit test evaluation. So the main problem here that is relying on public leaderboards alone can lead to costly and biased choices. Because these leaderboard selections are only reduced to the execution scores, so models are ranked mainly by the pass rates only. And this creates two issues. That first of all, these scores can be near tied. Several models may have very close performance and small differences in the benchmark that can lead to their ranking. And secondly, the leaderboards often make larger models appear more preferable. So this can create an anchoring bias towards the size. So where we assume that the largest is and the most expensive model must be the better option. So the risk is that leaderboard only selection gives a limited evidence, which can lead to a costly and a biased model choice. And this brings us to XPJudge. The central idea is the first ranked LLM is not always what you need. Instead of automatically choosing the highest ranked model or on a static benchmark, XPJudge supports selecting the most suitable model for a given need. It is built around task-oriented evaluation setting. For each evaluation instance, we consider three main elements. First, the task, which represents the requirement that the model needs to satisfy. In this study, we focus on software, so code generation tasks. And secondly, the solution, which is the code generated by the LLM under evaluation. And then thirdly, the explanation, which is the justification produced by the model. And this is important because it gives additional evidence about how the model understood the task and whether its reasoning aligns with the generated code. So XPJudge is not only evaluate the final code artifact, it also evaluates the dynamic between the task, generated solution, and the explanation. So here we compare the model pairwise and not pointwise. So the pointwise judged ranking can be problematic according to some previous work. So if we ask a judge model to score each solution independently, the absolute scores may be unreliable. LLM judges can be affected by confirmation bias, where they tend to agree with the provided answer instead of critically evaluating it. So to reduce the problem, XPJudge uses an explainable pairwise evaluation strategy. So instead of asking only what score does this model get, we ask between model A and model B for the same task, which solution is better and why. And with the LLM's wide variety, instead of making impulsive decision, we enter this loop of comparing candidate models, eliminating the least performing ones in a use case until we get the winner. So the idea is compare pairs, select the better option, and then use those comparisons to support ranking and model selections later on. So XPJudge has an overflow has a workflow of three main stages. In stage one, we select the tasks, candidate models, and the evaluation attributes. This defines the scope of the generation overall. Of the evaluation overall, sorry. In stage number two, we ran the candidate LLMs of the selected tasks. Each model receives the same instruction prompt and generates a code with inline comments and a self-explanation. So then we execute the generated solution against the unit tests to collect the functional correctness signals. And then in stage three, we use a dedicated LLM judge to score the generated outputs and perform a pairwise comparison. The judge evaluates both functional and non-functional software quality attributes, provides rationales, and selects the preferred model for each task. So this workflow has two advantages. First, it is less sensitive to judge bias than pure point-wise ranking because models are compared side by side. And then second, it requires less computation than a full pairwise ranking over many models since we pick the winner and the challenger pairs with nearly tied performances. So to start, let me go into the details of stage one. For the data set, we use a big code bench subset for this empirical study. It contains challenging code generation tasks that require deeper reasoning and more complex instructions, and a careful handling of edge cases. So in our study, there is 148 tasks and 848 unit tests. Then we define the software engineering attributes used for the evaluation based on a literature review. And we divide them into two categories. The first one is the code quality attributes or the non-functional attributes, and they are readability, maintainability, and reliability, and their definitions that will later on be included in the prompt are taken from the literature. And then the second group will be the task alignment attributes or the functional intent attributes, and they are functionality, relevancy, and semantic alignment. So for the candidate models that were selected in this empirical study, they have good coding abilities, and because they are diverse in family, size, and cost, and they were taken based from the ranking of the public leaderboard of a big code bench. Hard subset, of course. In this study, we evaluate three families. So we have Quen 2.5, Phi, and Gemma. And we include both general instruction-tuned model and the code specialized model. So this will give us a meaningful comparison of what is affecting the cycle overall. And the table shows the hardware and the cost setting. This is important because our goal is not only to identify the most accurate model, but also understand whether this additional cost of a larger model is justified by better software quality outcomes. So for stage number two, we start by each candidate LLM receiving the same coding task and a fixed instruction prompt, and then the model will be generating a complete implementation as a solution for that task. And the prompt asks the inline comments and a self-explanation as well. And after that, we run the task unit tests for each generated solution, and this gives us a consistent output format across both models. So we get to have the for each task model pair, the artifacts, which are the generated code, the self-explanation task, and the model metadata, and the unit tests pass rate as a baseline for correctness signal. And to have an idea about the abstracted generation prompt. This is kind of how it is being like put for the generational models. There's the task description, a generation requirements as what the model should do exactly, and then the output format, which is very important to later on extract the needed data. And for stage number 3, which is the core judge-based evaluation stage, here the LLM judge receives the task and the generated code and the self-explanation, and then score each solution from 1 to 5 for each software quality attribute, functional and non-functional. For every score, the judge also provides a short rationale. This is important for auditability later on. We do not only want the number, but also we want to know why the judge assigned that number. And then the judge performs pairwise comparison using the collected artifacts. So it compares the two models on the same task and selects the overall preferred model. So the judge reports the agreement score that tells us whether the two models produced a very similar solution or they follow different approaches. So this is kind of what the stage 3 is about, which is producing qualitative scores and qualitative explanation, making the evaluation more interpretable. For the judge prompt, it goes as follows. For the like an abstracted version of it, of course. So we have its role, the inputs that it takes, the model A output, the B output, the problem in general, and then the evaluation steps, and then the evaluation criteria, very well defined, and the scoring scale. And what we expect is this kind of JSON output of the model A, and then every software engineering attribute being rated and its rationale. And then the model agreement score overall and the better model and a feedback. So the judge model that was selected here is the Quen 32 billion, which is like a reasoning model. And because the LLM judge can have biases, we apply mitigation strategies. So model identifiers were masked. The judge is instructed on predefined rubric criteria, and the same prompt and judge configuration is used across this evaluation, and the scores are supported with rationales for auditability. And Quen also was a very high performance in this subset in particular when we evaluated that before we started this process. So the metrics are pass rates, the failed, the unexecuted, and the passed tests, and the fully solved, partially solved tasks, as well as the judge scores. And then for statistical analysis, we did the Spearman correlation that measures the alignment of the judge scores and the unit tests. Mann-Whitney to check whether the two models differ significantly on each attribute, and then Cliff data that measures the size and direction of the difference between the two models. So this brings us now to the results, starting with the first research question. So before using XPJudge and to evaluate richer software quality attributes, we first need to check if our framework aligns with if the functional scores are credible and they do align with the correctness, and the answer is yes. So we find a strong agreement between XPJudge functional quality scores and the execution signals. In particular, the Spearman correlation is 0.943, which indicates a very strong relation. And this means that the judge-based functional scores are not arbitrary, they are strong and they are aligned with the unit test correctness. And XPJudge also provides the additional information that was needed. So the unit test test pass rates tell us how many tests were passed, but they do not explain why. And this alignment and explanation, they were deducted from the XPJudge, and it adds through this evidence of functionality, relevancy, and semantic scores. We can see that, for example, Phi 14 was very well aligned, having 36 fully solved tasks and a high score of 3.6 nearly, and a pass rate of nearly 58%, which is, mind you, we already have a different ranking from the public leaderboard. For the RQ2, we ask whether the XPJudge can capture non-functional software quality differences that are not directly measured by the unit tests. And the results show that XPJudge gives a very consistent model ranking under both functional and non-functional aggregation. In other words, the model that better capture the task content also tend to produce code that is easier to read, maintain, and trust. This is important because it should suggest that good functional performance and good software quality are related on this data set specifically, but they are not still identical, as the attribute level score help us see how they differ. For example, some models may be strong in functionality and weaker in readability, and others may generate a simpler, more relevant code. So a key finding also here is that code specialized models rank higher than the under the judge-based score. This suggests that specialization improves not only functional performance, but also the adherence to software quality expectations, no matter what the size is. And the third research question that focuses on the pairwise model selection. Here, XPJudge compares models head to head and selects the preferred model of every task. And the results show the following. That pairwise evaluation can produce this decision-oriented preferences, and it contradicts the leaderboard-driven expectations. For example, Qwen 2.5 coder B instruct is preferred over the 2.5 instruct 14 billion in 56.1% of the tasks. And this is interesting because 7B is smaller but code specialized. And then Qwen Coder 40B instruct is preferred over the Qwen Coder 32B instruct in 58.1% of the tasks. This shows that the larger model is not always preferred, even within the same code specialized family. And then for the third pairing, which is Phi4 14 billion, is preferred over Gemma 27 billion in 60% of the tasks, despite Gemma being larger and requiring more GPU. So these results support the main message, which is smaller or a specialized model can often generate simpler, more relevant solutions, which without sacrificing the functional performance. So XPJudge here help us kind of identify the practical deployment trade-offs that are not visible from the leaderboard rankings alone. So to summarize and put them in like clear takeaways here, a perfect solution would be high on both dimensions, which are the task alignment and the code quality. And in this study, we see that large models, yet reliable, are in cases irrelevant and complex. And on a second note, some small specialized LLMs may be functional, relevant, readable, but they can still be a little brittle in some cases. That means that they may perform on many tasks while still failing on some edge cases or that require complex specifications. So the conclusion here would be that the bigger the LLM, the better is not always true. So public leaderboards often reinforce this idea, pushing us that the highest ranked one is the best choice. But XPJudge here shows that the winning model were not always the usual suspects, as you can see, since that's the table of the public leaderboard. And on the left, you can see the rankings of the study. And in our results, the co-specialized one were preferred over the larger ones, and the larger ones did not consistently produce what we want to say a better output. So this supports the need for a cost-aware model selection. And for future work, we want to improve generalizability by using multiple judges and also measuring the agreement between these judges. And why not extend it on more benchmarks and see more realistic software engineering tasks, like you were saying earlier, that this is maybe only file based problems, but when we see the SE as a whole. So it'll be interesting to see how this framework performs. So that's like the link of the published paper as well as the code. And thank you so much for your attention. I am open if there's any question.
Thank you so much, Yasmine. Excellent presentation, very clear and comprehensive research.
Thank you.
So yes, you can take questions. Bram, would you like to start?
Yeah, great work and really interesting. I'm wondering on slide 16 where you show this high correlation with the execution-based correctness.
Mhm.
Does that mean, so is that kind of like an ablation you did to figure out which of your three dimensions mattered the most in the final decision? And if so, does it mean that actually the explanation part is less important than just the test result part, or how to interpret this correlation?
Well, first of all, the way we ran the models and we generated the code is different from how the leaderboards do it. So we did it like separately, and we had that study separately. And since then, the ranking already changed, and it does not. It's not very coherent with what the public leaderboard is saying. And with that change, the judge scores supported the ranking that our unit tests did, and not the ranking that was in the public leaderboards. So that's how they correlate.
Okay, but so you took a separate benchmark that was not in the leaderboards. You ran a thing using your approach, and then you found a correlation of the judge's result with the actual unit tests of your
Yeah,
benchmark. But does
yeah.
that mean actually that the other dimension you had, like the use of explanations, and there was like the task description, that those two factors actually don't really matter that much in the judge's output. It's more just the result, the execution, the test results on the benchmark.
Well, the explanation matters because one of the SE attributes that were like scored are the is the alignment. So that explanation that the candidates generated was used by the LLM judge to put out that score, which is actually not here. It's gonna be in this area, which is a non functional quality.
Mhm.
So that's where the explanations were used.
And do you know what was actually the right answer? Like what would have been the best model to use? Did you have like a ground truth there?
Oh, no, that's the thing. So XPJudge doesn't really give us a ground truth. It's more like a framework where you can give it a certain task. Here I chose like SE tasks and code generation, but it's a general explanation judge where you can select a given task and then give it two models, and it will do the whole pipeline of prompting those candidates and having the solutions and then evaluating them and giving the user which model performed best at that given task. So it's literally like a first like step and a framework to use before you start implementing it in work.
Okay, so people would first look at the leaderboard, make a short list, then apply your technique, and
Yeah.
then the winners they would continue and do deeper analysis essentially.
Yes, to see if it's
Yeah.
worth to see if it's worth paying an expensive amount of money on a larger models or not,
Oh,
mainly.
okay, that makes sense. Yeah, cool. Thanks a lot.
Okay.
Thank you, Bram. Does anyone else have any other questions for Yasmine about her presentation? Questions or comments or feedback? Both Yasmine and Anne will be defending their master's thesis very soon. I think right after our program retreat in July. So I have no doubt, based on what you've delivered today, that you'll both excel in your master's thesis defenses. So I'd like to wish both of you the best of luck.
Thank you.
And if nobody else has any other further questions, I guess we can wrap it up for today. Oh, some of our guests are wishing you good luck as well.
Thank you so much.
Yes, great work. I agree. Great work, Anne and Yasmine. Thank you so much for doing your CREATE Trainee Talks this morning and sharing your research with all of us. And thank you everyone for joining. We'll be back again in September with more research talks from our CREATE program trainees. So in the meantime, everybody enjoy the World Cup and cheer on Team Canada later today.
Thank you, everyone.
Thanks, everybody.